All right, this week we're going to talk about the last two topics in numerical methods. But today, in this video, I just want to talk about numerical integration. So integration, an integral, is analytically an antiderivative, and so they're opposites of functions. If you were to take the derivative of an integral, it would cancel each other out. So if you've taken any calculus, taken EGR 1010, you'll have probably somewhat of an idea of what I'm talking about. If not, don't worry about it, because what we're going to worry about is, all right, so how do you approximate them? How do you, much like we did with derivatives, how do you approximate an integral? And in particular, we're going to look at how do you approximate a definite integral. And if you did take calc, I think probably 2, I think they cover integrals. It might be the end of calc 1. The first thing you use is what's called a Riemann sum. And so you're trying to approximate this area with rectangles. And if you look on the right, I have this video showing you how they're approximating it with smaller and smaller rectangles. And like the proof and derivation for how you can actually do an integral is you take the width of these rectangles and bring them to 0. And so eventually that would turn into this the entire solid area and include everything. What we want to do, though, is we want to approximate it by splitting the area into smaller, easily calculated areas. And so in this case, it's going to be, the first two is going to be rectangles, then we're going to use trapezoids, which is actually a slightly more accurate way to approximate them. And so let's say, all right, we're going to have two different types of rectangles. One's going to be called an inscribed, one's going to be called a circumscribed. And that's going to be dependent on which point you're using to approximate the area. And so the inscribed rectangles use the left-hand point. And so if you notice, we calculate each of these areas and then would add them up. And each of the areas are just base times height. But if you're using the left point, the first height is going to be 0 because it's crossing 0. The second one would be H2, H3, H4, and H5, and you're all multiplying by the base, whichever width on the x-axis you have. Typically, that's a uniform width. And in the cases I'll probably be doing, it'll be all uniform width. So it's all going to be time times some interval constant times the height, which the height is going to be whichever side of the function you're choosing to use. One thing to mention is that you usually have one unused point if you're using these rectangular methods, because if you're using the left-hand side, because there's n-1 areas, there's always one fewer area than there are number of points. So one point or one height is going to be disused. And so in this case, since we're using the left-hand point, you get to the end and you don't end up using this last data point. In the circumscribed, you have the opposite, where the unused data point is the first one, because in your first rectangle, you're always using the right-hand point. So in this first rectangle, the point is the second point. The height is the second point. Then H2 is the third point, H3 is the fourth point, all the way to the end. But you're still using the same equation, base times height, and then you're adding them up. And so to find the integral at each point, so let's say that this is the derivative of some function. This is velocity, and you're trying to calculate position. To integrate it and to find like each point, you would basically take the previous point, add the area, and get to the next point, because that's effectively how you determine a function from its derivative, is you take the integral and add some initial condition. And so I'll get to that later. But what I want to mention with these rectangles and with all of these is you're always going to use a for loop to calculate these, either the sum or to calculate each point as you go. And what you want to do is you want to go from the first point to n-1, because no matter what you're doing, if you've noticed, you're not going to use one of the points. So you have to go across the range but stop with 1 point less, because eventually you might get to, all right, I'm going to go to I plus 1, and if you go through n areas, the number of point areas, you're going to end up with an error because you don't have data where you need it. And that could be if you like in this case, if you tried to calculate like here, starting at H1, you're going to use the previous. You're trying to try to use the previous point, and you can't. It doesn't exist. And in this point, you'd get to the last point here, try to use the next area, and you don't have that. There's no data there. So you always have to go to n-1, and I'll show you that when I build the code. The third option is actually, like I said, more accurate, and so you end up having a trapezoidal approximation. And what that means is you basically are just calculating the area of a trapezoid, which is a very similar calculation. You're just averaging. So at any given area, you're averaging the point to the left and to the right of it, and then multiplying it by the base. So like in this case here, the area of this would be B3 times the average of H3 and H4, or H3 plus H4 over 2. And so this is kind of the general equation. You end up using all the points. You still want to go to n minus 1 because you only are calculating 1, 2, 3, 4, 5 areas for 6 points, but you're still using all the points with this method, which is one of the reasons that it is more accurate. And as you can just tell, it much more closely approximates a curve, especially as you get smaller than a rectangle does. All right, and so these I'm not going to show examples of, but I want to show you, all right, so that trapezoidal method I just showed you, you can do the same thing with a traps function in MATLAB. I'm going to show you how to do it hard code because it realistically, the traps function doesn't save that much time, and I'll show you why as I'm doing it. But the traps function is nice. It allows you to calculate the area under any curve, any data, any analytic curve, like here y sine x. All you got to do is give it the x and y data, and it'll give you the entire area. And so that's one way you can calculate a definite integral. Another is if you have the actual function, you don't just have data. You can do as we've done before, define an anonymous function for your equation here. And so like in this case, this function that I gave you as an example, I'm not going to run it, but you have it here if you wanted to go play with it as an example. This e to the negative x squared times sine x doesn't, I don't think, have an analytic solution. So you couldn't take the definite integral of it very easily, right? Because it doesn't have an analytic solution. You'd have to represent it in a different way and then do an analytic integral. But instead what you can do is you can use the integral function in MATLAB, define it as an anonymous function, plug it into this integral function under the first input, give it an x min and x max, and it computes the definite integral. And so what might be nice for you is as you go through, take the calc sequence, and you have to do like definite integral homework or whatever, and you need to check your answer, this works. It's not going to give you the analytic solution, it's not going to give you an equation, but it'll give you a number. So in this case, I went from 0 to pi, and the answer of the area under this curve here was 0.4244. And so that's kind of the things we're looking for. And so I just kind of rocketed through all of that because really all it is you're calculating areas. And so what I want to do is I want to, given this data here, this is time and acceleration. And I've kind of explained, I think in the last week's lectures, the relationship between acceleration, velocity, and position. What I want to do is using this acceleration data, it's kind of the inverse of what I did before. I want to calculate the velocity and the position, given that the initial velocity initially at rest, or it's equal to 0, and the initial position x is 0. I want to do it using the three methods I just briefly explained to you. So using inscribed rectangles, circumscribed rectangles, and trapezoids. And I want to recall what this right here. And so this was just kind of a reminder for you and myself that that velocity it can be calculated by taking the integral of acceleration. And so what I want to do is I want to calculate the velocity and position at each point if possible. So I know it at 0, but I'm going to calculate it at each point. And so the way you do that is the velocity at a point is you use the previous velocity and then calculate the integral or the area between those 2 points. So the velocity at point 2 is approximated by the velocity at point 0, which is 0, plus the integral between 0 and 2 of the acceleration. And then you do the same thing for x. So I'm going to set this up for velocity, then I can, as I've done before, copy and paste for x because the equation is exactly the same. Because position x is the integral of velocity. And so I'll walk you through these. And I'll do them one by one. And so let me grab the data here. I'll type it for you. So I'm setting up the initial velocity is equal to 0. The initial position is also equal to 0. Those are important because they'll be used to start this kind of method here. I define my time vector and my acceleration vector. And so in this, I can say my base for each of my rectangles and trapezoid is 2 seconds. So that's good to know. That makes my equations a little bit simpler. So the first one I'm going to do is an inscribed rectangle. Oh, sorry. Is an inscribed rectangle. I was actually going to go up here. And I can show you what the inscribed looks like. So the inscribed uses the previous point, right? And so I want to go back, and so the actual equation I'm going to use is this one. So I'm going to use a for loop and go through each point in the range up to, like I had told you before, n minus 1, because I can't use I'll show you why you go to n minus 1. It'll be easier than explaining it without it in front of me. So I'm going to go for I is equal to 1 to length of time minus 1. Remember, I tried to hit this point home multiple times. I'm going to n minus 1 because there are n minus 1 areas. But I'll still be able to calculate the velocity and position at all the points, you'll see. And so I'm going to do v of t2, which is going to be v of I plus 1. So that's v2. That's v of t2. T1 is starting at point 1. T1 is going to be v of 1 is equal to naught, right? So my initial velocity is this first point in my velocity area. It's the point that corresponds with time of 0. And then my next time is going to be equal to my previous time, v of I, plus now is where I use my calculation for the integral. And so with the inscribed, I use the left-hand side, right? And so it's going to be base, which is 2, times the left-hand height, which is acceleration of I. Because remember, this is the I is the left point. So if I look at it here, it'd be like I'm doing this first rectangle. I is this point H1. I1 is the H2, or corresponding with X2. And so when I go to circumscribed, it'll be I plus 1, and that's the only difference. But so I went through, and this will calculate all of them, right? It'll keep going through, and the reason you had to do the other reason you had to do length of time minus 1 is because once I get to this last point, if I were to try to do v of I plus 1, the acceleration of I plus 1 doesn't exist because it's a point past 51 that doesn't exist, right? I'd be trying to potentially pick out a point that I don't really have data for down the line. So you have to go only to the last one. And remember, in this case, I will not, with the inscribed rectangle, I'm not going to use this last data point, and that's exactly what it says here, right? Is I didn't use the last data point. And now I can do the same thing for x, which is going to be position. So I'm going to do x of 1 is going to be equal to x naught, so the initial position. And you have to be given an initial condition whenever you're doing integration problems. You have to be given one. And you also have to be given one for differential equations, because a differential equation is kind of like differential equations and integration kind of go hand in hand. You'll notice these forms when we get to differential equations later are going to look very similar. This for loop will look very similar to what we do later. And so I need to do the same thing. It's going to go to the same thing, length of time minus 1. But this time I'm going to use x. But the equation is the same. Plus 2. And now the only difference is going to be, instead of using acceleration, the position is the integral of velocity. So I just calculated velocity, and now I can do it for, now I use that and integrate it to calculate my position. There. And so that's the equation for the inscribed rectangle case. And so like I said before, these are going to look like very similar. So I'm going to do circumscribed rectangle. So here's the circumscribed rectangle. I'm going to underscore this VC. So, using the same for loop, I'll just rewrite it for you. VC of II plus 1, the next point that I need to calculate, because remember, I know my initial condition, so I'm just going to kind of work my way through the entire array, is going to be equal to VC of II plus 2 times the base times the acceleration. Instead of using II, I'm using II plus 1, because that in this case, so if I go down to the next slide. So now you look at it, and I'm not using the first data point now. As far as using it in the, I'm not using the first data point to calculate my areas. I am using it. I still have to use that for my initial conditions. And there, so that will calculate it. Now I just need to do the same thing for x. I'm going to change these subscripts to c. So c means the underscore c is for circumscribed. And then you take the integral of velocity, but remember we're using the circumscribed case, and so you're using the next point to calculate as the height of the rectangle. And that's the only difference. And the last one we're going to do is for a trapezoid integration. And so the trapezoid integration, I'm going to underscore all these to be t, but I'm going to rewrite this. So I'm calculating the next point. It's still going to be the previous point, so VT of II plus, now I need to calculate the integral. And the integral for the trapezoidal case is you take the average of both of them. So this is going to be a much longer equation. So I'm going to still multiply by the base, but now I need to average the values. So it's basically going to be, I'm going to kind of take an average of these two cases I've already done. So the first one's going to be acceleration of II, so the left point, and then the second one's going to be the acceleration of the right point, then averaging them by dividing by 2. So that's this equation. X of I plus X of I plus X of I minus 1. Oh no, I'm saying this all wrong. So f of xi plus f of xi plus 1 divided by 2 times delta x. Delta x in this case being 2. And so now I'll have to do the same thing for my x values. I have my initial condition. The next point is equal to the previous point plus base times the average of VC of II, so the left point, plus the VT, sorry. I just calculated VT of II plus VT of II plus 1, the right-hand point, divided by 2. And that's the area. These two are both areas of trapezoids. That's just an equation. And so here I said, all right, here's why the traps function is not going to be as efficient, or it's not going to be much more efficient. It's because all I would do in this case is I would replace these area equations with traps. And I'd still have to know exactly what I'm doing. I still have to input the data points. And so I really wouldn't even be saving that much space. That's just as an FYI. Where it's more useful, it's not useful in these cases where I'm parsing through the entire thing and actually trying to come up with the entire function. If I were trying to calculate the entire area, it would be faster because I'd have a vector of data for both. So what I could have done is if I wanted to find the entire area under this curve, and using the traps function, you would just input these in directly. That's when it saves time. A case like this where I'm actually trying to do the antiderivative, I'm trying to find velocity and position, the whole function, every point, it's not any faster. It's actually, honestly, it's a little slower because you'd have to figure out how to do it. It would take more time than just using these equations, which I've been showing you. All right, and so let me go down. I think I've basically solved this equation, and what I can do is I can plot them for you if you'd like. I guess no one can tell me if you'd like me to or not, so let's do it real quick. So I just want to plot, I'm going to plot the 3 different velocities. So I'm going to do time, and then it's going to be v is the first one, and I'm going to make that one be black, time, VC. So the first one's inscribed and circumscribed, which I'll make that one be blue. And then the third one is going to be time trapezoidal, and that one will be red. And then I can do the same thing for x. we'll do figure, and I'm not going to waste too much time formatting the plots because it doesn't really matter. I just want to show you that the are going to be very similar. So this will be x, x, x. And they are. They're similar. So, but they actually end up being also fairly different. So the red line is between the two. So if you remember me saying the red, the trapezoidal, and I keep saying average, right? The trapezoidal case, the equation for trapezoidal, it's actually the average of the other two functions. And if you look at it, that's exactly what happened for both velocity and position. The red is right in the middle. It's the average of the two. And so in this case, it looks like, so the black one was the inscribed. The inscribed underestimated, the circumscribed overestimated, and the trapezoidal one is probably much closer. But you can see they're all similar trends. They have the same kind of shape of curve, and they all have the same scale. So that's what I'd be looking for. If they were very different, the scale would be different, right? But they're all the same. Their units are effectively all the same. So the position is effectively an order of magnitude higher than so it's times 10 times the velocity, which makes sense. So you end up integrating and you end up multiplying over time and you get bigger numbers. And so all these look good. So the red curve is indeed the average. And so like I said before, if I myself were to write something and use it a lot to integrate functions, to integrate data, I would probably use the trapezoidal integration just because if you know it kind of splits the difference between the circumscribed and the inscribed. But all of them are valid methods of approximation. And I'm sure if you take numerical methods later on in your careers, you will find out exactly how to approximate, like how accurate are these. But we're not going to worry about that right now. And so what I want you to do is do this problem. So using the inscribed rectangles, circumscribed rectangles, I want you to integrate the following functions to find the definite integral from 1 to 5 of this function right here. And then I want you to plot the comparison of the, well, and then you can actually solve what the actual integral is from here. All I'm going to ask you to do is find the area under the curve. You don't have to actually plot it. So I might go change that. But the initial value is 4, and the step size is 0.5. So I just want you to find the area under this curve from 1 to 5 using a step size of 0.5, using inscribed, circumscribed rectangles, and the traps function. And that wraps up integration.